Hello, everyone. My name is Dylan Walter, and on behalf of my team members, Diego Conterno, Tyler Michaud, and Alejandro Porcar, we are Senior Design Group C. Our project is called the ADEPT, or Analog and Digital Effects Processing Technology. First, let's outline our goals and objectives for the project, starting with our project motivation. As engineering students, as well as musicians, our team has decided upon a senior design project based around audio engineering, music technology, and sound design. Throughout this project, we have been able to apply the engineering fundamentals we have learned throughout our respective undergraduate degrees into something we are passionate about. Closing the gap between technology and music, we are providing a new alternative for musicians who want to stand out and shape their sound in a unique way. We are providing a digital multi-effect solution that will have a creative impact not only on musicians, but also those with an interest in electrical and computer engineering. Since our project is open source, anyone with the necessary know-how can utilize our platform to develop any DSP audio effects they could possibly think of. Next up, our goals and objectives for the project. Our compact design is the perfect size to fit on any musician's pedal board, alongside other music gear. Our pedal was designed to be as affordable as possible in order to compete with the many boutique guitar pedals available on the market today. Not only should an aspiring DIY enthusiast be able to afford all the components of our project, but it should also be easy to assemble and to use. With a simple user interface and parameter controls, the ADEPT is foolproof. On the more technical side of things, we designed our project to draw as little current as possible. This is important in order to maintain compatibility with the standard 9-volt, 100 milliamp pedal power supplies available today. We also made sure that we are only hearing the effects that our unit will apply to our instrument signal, without any unwanted noise. The ADEPT has a signal-to-noise ratio of 15 decibels with clear signal quality. Last but not least, the ADEPT is reliable. By utilizing high-quality components and a strong metal enclosure, musicians will be able to rely upon our product to function as it should, even when performing in harsh weather conditions or when stomping on this effects pedal night after night. For our project's requirements and technical specifications, we are utilizing a list that includes not only fundamental technological prerequisites, but also some more advanced aesthetic features. The technical requirements we have implemented in our design include analog to digital conversion, high input impedance, low output impedance, and standard connections that include quarter-inch instrument cable inputs and a 9-volt center negative power cable input. Some of the aesthetic design requirements we have implemented include looper and dual foot switch functionality, JTAG and SWD programmability, and an LCD user interface. For our technical demonstration, we will be highlighting 3 key requirements, including analog to digital conversion, JTAG and SWD programmability, and the LCD menu and selection screen. Here's a high-level block diagram of our project's major components. Later on in our presentation, we will discuss each team member's individual responsibilities for the project. Now we will discuss our system's hardware and PCB design. Here's the overall schematic layout of our design, created using Autodesk Eagle. For organizational reasons, we have divided the schematic up into multiple sections that pertain to each of the major components of our project. These components include our power supply, input and output buffers, codec, MCU, LCD screen, external oscillators, flash memory, and our tone and volume controls. For our PCB layout, we decided upon a 2-layer design for simplicity and cost. The default trace widths and spacing specified by the Eagle software were used. In order to reduce potential signal noise affecting our external oscillators, we made use of multiple restrict layers in order to prevent traces from being routed anywhere near these sensitive components. The dimensions of our PCB turned out to be around 116 by 88 millimeters, which was an acceptable size to fit inside of our enclosure. Our PCB fabrication was done by Osh Park. We used both surface mount and through-hole components in our design. Here you can see a mock-up image of our final PCB design. For our enclosure, we used a Hammond 1590XX enclosure size. We made use of Autodesk's Fusion 360 software to create a 3D model of the PCB enclosure, such that we would be able to make precise measurements based on the dimensions for our components and the PCB itself. As mentioned before, our pedal has dual foot switch functionality. This means that we have a primary foot switch to turn the chosen effect on and off, and a secondary one that can be assigned various specialty functions. One of these functions that we implemented was using the foot switch to start and stop the recording of an audio loop. For the primary foot switch, we are utilizing a 3-pole double throw, true bypass latching foot switch. For the secondary foot switch, we are using a single pole, single throw, momentary foot switch. These plunge type foot switches are the standard for guitar effects pedals due to their ability to be activated hands-free. We are also utilizing two 100 kilo ohm potentiometers to adjust both the overall volume of the pedal's output and the tone of the applied effect. The tone control is created by implementing a simple first order RC low pass filter that will adjust the cutoff frequency of the signal as the potentiometer is turned, thus making the sound of the effect brighter or darker. During our research, we compared a few different tone control configurations, but ultimately decided upon the blues breaker style tone control for its simplicity and low cost.
So this section is for our input and output buffers. Buffers are basically used to drive a signal through a medium without attenuation. Buffers have a current-driven signal, and they turn it into a voltage-driven signal. This was essential for properly passing our analog signal from the guitar to pedal and from the pedal to the amplifier. For optimal performance, we designed our buffers to be impedance matched for the device each buffer was connected to. In our case, the buffer's output connected to the input of the input buffer and the output buffer's output to the input of the amplifier. For this reason, we designed the input impedance of the input buffer to be high, since the guitar's output impedance is high. Similarly, we designed the output impedance of our output buffer to have a low output impedance, since the amplifier's input impedance is low. Other buffer configurations we considered were the JFET and op-amp buffer. Our decision came down to a trade-off between price and loss at the output. As you can see, the emitter-follower configuration only had negative 0.13 decibel loss compared to the other designs. Negative 0.13 decibel loss is negligible in our case, since it isn't that really high in magnitude on linear scale. That, along with its cheaper price, made it the ideal design. Emitter-follower configured buffers are commonly used in the guitar pedals on the market. Fortunately, we made a good decision using this, since our design gave us no issues when testing on our pedal. As you can see, we made a table comparing the cost, complexity, and performance of each buffer configuration. So for our input and output impedance test, we basically got a spectrum analyzer or an impedance analyzer, and we measured the output of the output buffer and the input of the input buffer. And we basically matched them up with our small signal analysis calculations when we were designing our buffer configuration. Luckily, our input and output impedance measurements were accurate to our calculations. For powering our guitar pedal, we used an isolated DC wall plug-in with a coaxial power jack. Our 9-volt source was used as a master power source for all devices on our PCB. We used two step-down voltage regulators of 5 volts and 3.3 volts, along with a voltage divider with an output of 4.5 volts. The 5-volt regulator powers the LCD and is used as a voltage reference for the codec. The 3.3-volt regulators powers the MCU, flash memory, rotary encoder, and the codec. Furthermore, the 4.5-volt voltage divider set our DC bias for our input and output buffers. This block diagram represents the distribution of power in our system. When selecting voltage regulators, we found that it came down to a trade-off between noise and power efficiency. The major decision was if we wanted to implement a switching or linear regulator. Switching regulators are typically noisier due to the switching at the output. Linear regulators are by far less noisy and less expensive. Since we aim to preserve good sound quality and are using external power and not battery power, we chose to sacrifice power efficiency to reduce noise in our signal paths. For simplicity, we chose the LM1117 for a 3.3-volt regulator and the LM7805 for a 5-volt regulator. For a power transient response test, we used an oscilloscope to observe our board's stability when powering on and off. We measured the 9-volt input and regulated 5-volt and 3.3-volt outputs. We specifically wanted to see if there was any overshoot or damping effects during power on, along with undesired ripple during power off. We also wanted to make sure that our power on time was fast enough to appear instantaneous to the user. The total time our pedal took to completely power on was about 80 milliseconds, which would indeed appear instantaneous to the user. We wanted a signal to noise ratio of about 14 decibels. To confirm this, we measured the magnitude of the signal and compared the ratio of the magnitude of AC ripple along with our original path in logarithmic scale. We measured a signal to noise ratio of about 14.92 decibels. Our measured signal to noise ratio was better than our desired value by about approximately 1 decibel. A low signal to noise ratio can lead to bad sound quality. For example, a signal to noise ratio of 0 decibels would mean that the magnitude of the noise is equal to the magnitude of the signal. This would be catastrophic to sound quality, so it was important to confirm that our signal was strong enough to negate any noticeable noise.
The options we were looking for are MCU, vary in terms of memory, processing power, DSP functionality, and overall functionalities. We decided to go with the STM32 not only because of the cost, but also because it packed an array of features such as the 3 SPI lines, 2 of which could be used for as I2S, plenty of processing power, and an FPU that could be used for the processing of effects. The amount of GPIOs, timers, functionality in terms of software applications was also a huge plus. The STM32F446 is one of the many in the lines of the STM32F4s. They pack a Cortex M4 processor, which provides an exceptional performance, which is to be expected of a modern 32-bit architecture. It has a clock frequency of 180 megahertz, which is more than enough to process the bit stream received by the codec from the incoming audio signal. Although the STM32 does not have a DP unit, it contains a floating point unit, which means we can rely on it to compute the operations required for effects functions without the use of a library. This will increase the performance significantly. We're excited to show you the results we have achieved using it. Another feature of this MCU is the integrated configurable debug. This provides a high system visibility of the processor and memory through either a traditional JTAG port or a 2-pin zero-wired SWD debugger.
In order to handle our conversions between the analog and digital domains, we included a codec into our design, which is a chip that contains both an ADC and a DAC. We looked into a few high-performance options, such as the MAX 980, but it seemed to be a bit too complex to configure with many extra settings we didn't need. Another good alternative was the TLV 320, but it was only in stock for a higher price than our other very capable options. We chose to stick with the PCM 3060 because it can handle audio samples of 24-bit resolutions at our desired sample rate of 48 kilohertz. Its configuration programmability through I2C and affordable price. In order to interface and transmit audio back and forth, we use I2S protocol, which is compatible with our MCU. We decided to use an external flash memory because we needed the extra storage to have enough room to record audio, libraries, and extra effects. We chose this option over an SD card because of affordability and since we wanted to keep our design as compact as possible. The recording audio frequency we are trying to reach is that of 48 kilohertz with a sampler of 24 bits. The recording audio frequency we're trying to reach is that of 48 kilohertz with a 24 bits resolution. If we do the calculations, 1 second of audio recording will equal to 144 kilobytes. Now, the usual recording time for a guitar loop is between 10 seconds to a minute. Since our chosen Winborn flash memory has a capacity of 16 megabytes, we'll be able to record up around a minute and a half of audio.
Let's move on to the software design portion. For our software portion of the presentation, we have divided the following topics between Alejandro and I. Our goal is to explain the most relevant portions of our system in a clear and concise manner. The STM32Cube IDE and how. The IDE we used for the development was the STM32Cube IDE. This is the STM32's flagship IDE, which includes the STM32CubeMX software. This latter one provides the user with a graphical software configuration tool for GPIO and clock configuration. The IDE provides auto-generated code based on the configuration done in the graphical user interface, mainly for the configuration and initialization of the GPIOs and the DMA. The HAL drivers include a complete set of ready-to-use APIs that simplify the user's application implementation.
Testing and debugging tools. Having a reliable test bench such as the Nucleo board was the best way to make our firmware and development most efficient. Having the same MCU as our PCB, we were able to start implementing the software before our PCB was finalized. We used the STM32Cube IDE debugger tools such as breakpoints and live expressions watcher to solve issues within our code. Moreover, we utilize oscilloscopes and other lab tools to analyze clock frequencies and input and output signals. to check for logic and communication discrepancies.
Firmware system concept. The two-state machine diagram shows the non-conclusive nature of the system. The system is mainly driven in a state of listening mode, which refers to the state in which we're storing and incoming data from the ADC component of the codec, processing it, and then transmitting it to the DAC component of the codec. The system will remain in a constant listening mode unless we decide to press the reset button or power it off. Many browsing using the rotary encoder will not interrupt the auto processing. When one of the effects is selected, the system immediately applies the corresponding DSP function to the values stored in the audio buffer. UML and firmware architecture. Our firmware architecture is based around a few interrupts that trigger the DMA1 callback when the audio received buffer is filled halfway or fully filled. During these two callbacks, we apply the ping pong buffer algorithm and process the data. The encoder interrupt is triggered only when the user selects a new effect or looper mode in the menu. Although we pause and resume the DMA during this process, there is very minimal data loss since this happens in microseconds. Finally, the interrupt we have implemented is that for the switch designated for the looper mode. This interrupt only gets triggered when the user has selected looper mode in the menu. Otherwise, the looper and record playback functions will not work. In the case that the looper mode is selected, the interrupt for the switch will then increase the looper state and cycle through the process of recording and playback. Those two functions are fired in the while loop. Aside from these primary functions, our code also includes the corresponding logic and functions for applying effects, traversing the menu, and updating peripherals.
Clock configuration. We included an 8 MHz crystal for stability of the MCU in order to have an external clock reference other than the lower speed internal clock. We also used a 12.288 MHz crystal oscillator to provide our codec chip with the right clock for it to function properly when sampling at 48 kHz. Peripherals. We included a 16:2 LCD in our design for the user to get some visual feedback when using the device, scrolling through the effects menu and changing parameter effects. We use potentiometers as dials to adjust parameters available for each effect, as well as volume and tone control. We implemented this by giving the potentiometers 3.3 volts to the input and reading the output with the on-chip 12-bit ADCs. We then scaled the ADC output readings between 0 and 99 before displaying them. We included an encoder to give the user the ability of traversing through the effects menu in both left and right directions. We implemented this functionality using 2 channels of a single timer to determine the direction of rotation. Lastly, we used our SPST switch for prompting the looper feature commands of record and playback. For this implementation, we use an external interrupt to detect button clicks and then a timer for the bouncing purposes. Codec and MCU audio data transmissions. First, we use the I2C protocol to write to specific registers of the codec and configure the chip out of low power mode, as well as setting it to master for the I2S communications. To handle audio transmissions, we use the SPI lines in I2S protocol, which uses half duplex mode. We enable DMA mode with a data size of half words for the retrieval of data from the peripheral and out of it. The codec sends and receives on 24-bit samples on a 32-bit frame. The process of sending and receiving is done by using 2 audio buffers of size 2n, 16 bytes in total, where n is 4, which is a single sample. Thus, this transmission is done in a sample-by-sample basis. Data transmission between the flash memory and MCU. The communication with the flash memory is established using the SPI protocol, where we send and receive data byte by byte. When writing to memory, we utilize the data from the receive audio buffer, which is composed of 8 and 16-bit units. Thankfully, there was no need to decompose or recompose every audio sample when storing or retrieving from the flash memory. We also made a couple of helper functions that facilitate the process of writing and reading from memory. Additionally, functions such as flash read include a circular buffer algorithm that help with the retrieval of information in an organized manner.
Memory management. In order to cut down the memory cost that comes with the processing of effects, we have implemented DMA for storage and retrieval of data from the audio buffers. This way, the processor only has to take care of applying the effects. The DMA acts as a bypass for transferring received data samples into the SRAM, retrieving for the effects processing, and transmitting out to the codec. We also included an external flash memory mainly used for the looper functionality. However, it can also be used to store large sample buffers for effects such as delay and reverb effects. The all-pass filter shown is analogous to the all-pass filter from analog filters. As the name implies, it allows pass of all frequencies. In other words, the amplitude response of an all-pass filter equals to 1 for all frequencies, while the phase response can be arbitrary. For our implementation, we have changed the gain parameter to 0.7. The output signal of the guitar resembles the sound of someone playing through a pipe, hence the name pipe. The implementation we utilize for our delay simulates that of a feedback comp filter. This particular comp filter is an IIR, recursive, digital filter, since there is a feedback from the delayed output to the input. The resulting signal output will sound similar to that of an echo, or, if you will, a sound bouncing between two closed walls. As seen in the diagram, the reverb filter is a combination of the previously shown comp filter and the all-pass filters. This configuration is also known as Schroeder's all-pass section. There's many different ways of implementing Schroeder's reverberation algorithm. The implementation we use has 4 comp filters in parallel that are then normalized by a factor of 0.25, which then brings the sum to a series of 3 all-pass filters. There is also a feed-forward that allows us to implement a parameter of dry-wet, allowing the user to determine how much of the clean signal will be added to the output. To reproduce the effect of distortion, the original signal must be hard-clipped at the top and bottom of the wave. As shown in the figure, to achieve this digitally, we implemented a program where we can amplify the incoming signal as well as specify the thresholds of plus VCC and minus VCC, such that the amplified signal will be distorted, clipped at the top and bottom of the signal waveform. From a musical point of view, pitch shifting corresponds to the shift of a melody 1 or more semitones up or down. Now, from a signal's point of view, pitch shifting consists of scaling the fundamental frequency and its harmonics by a specific factor. The way this is implemented in the code is by utilizing a circular buffer that introduces every new sample and sums a value, the shift desired, to it, thus returning a scale version of the sample. The goal of a compressor is to gradually reduce the overall gain of an input signal if it is past a certain threshold. The compressor has 3 main parameters: attack, release, and hold. If the input signal jumps to a higher level above the threshold, then the attack phase is initiated. Attack means that the audio input level is reduced step by step over time until the final gain reduction is completed. The attack parameter is set to a specific time in milliseconds. Once the signal level is below the threshold, then the compressor recognizes this and waits for the hold time to set the signal back to 0 dB gain. In other words, a gain of 1. Over the time of the defined release time, the audio signal is not manipulated anymore.
We decided to lay our controls as seen on the image, with the LCD being at the top of the device and with the 3 effect parameter dials right below it. Following it downwards and from the left to right, we have the volume dial, then the menu selector dial, and then the tone control dial. Lastly, at the bottom, we place our 2 foot pedals with LED indicators at the top of each. The left one can be pressed to toggle between clean and modified sound, and the right one for prompting our looper functionalities. Here we can see the finalized product of our prototype, following the layout explained in the prior slide. We use an aluminum encasing to protect all of the electronics, as well as to get rid of any outside factors that could introduce noise to our signal. When it comes to the user interface, we went with a very simplistic menu, similar to traditional market guitar pedals we have seen. Upon power up, the screen displays a short animation with the name of our pedal. Next, we jumped right into the main menu, where we can see the specific effect selected, and the user can scroll right or left using the rotary encoder. Below the effect name, we can see the parameter values that we can control with the top 3 dials, which adjust different sound aspects depending on the selected effect.
Project planning tools. We were able to stay consistent and meet weekly goals using Notion. We used it to track our progress by setting a timeline of milestones and breaking down each one into smaller measurable tasks. GitHub for sharing our code and keeping proper version control. We use Google Drive to share and store relevant files of our project, as well as working documents in parallel. We also use Discord and WhatsApp to stay in constant communication for the times when it wasn't possible to meet in person. As previously mentioned, Notion provides us a simple timeline for setting our progress and recording our milestones. Here's a picture of it. Cost of materials. Here we can see that the total cost comes down to under $150, which is an acceptable price for a guitar pedal. Progress percentage. In terms of progress, we're happy with the overall completion of our project. Although we ran into a couple of roadblocks in terms of firmware implementation, we were able to complete an acceptable number of effects for our demonstration. Challenges. Improper voltage of a 5-volt level was sent to the MCU, which has a max voltage of 3.8 via parameter control potentiometers, which resulted in a hardware failure for our first PCB prototype. ADC pop parameter jitter due to external clock. This issue has not been resolved, but it can easily be solved using a firmware update. Codec MCU communication setup. We face technical difficulties when trying to properly communicate with the codec and the MCU. This was mainly due to a couple of points. One, the STM32F4 set has master, resulting in an unsuccessful data transmission. Clock configuration for the codec requiring an external clock in order to be set as master in the communication with the STM32. Adjust the communication configuration of the I2S and DMA, the word size and data frame of the transmission. Implementation of the input and output buffers utilizing DMA interrupts and ping pong buffer. Codec and encoder interrupt conflict. The conflict between the codec and the encoder turned up when we started a proper communication between the codec and the MCU. This conflict was resolved by compiling a new version of the code and rewiring our system. Loss of code base. Thanks to the version control, we were able to recover a great part of our progress. We were able also to reconfigure the system by reverse engineering the current breadboard setup. Flash memory MCU communication setup. Non-blocking and blocking APIs effects on writing to the memory. Blocking APIs for SPI were utilized instead of DMA. We were able to read and write multiple times to different sectors of the flash memory without any conflict. However, we weren't able to retrieve the data at a proper speed for playback. Intrapersonal relations. Stress and anxiety from the complications mentioned above gave rise to conflicts among the team. Solutions to overcome these issues provoked a difference of interest. This was solved with in-person team meetings and constructive reasoning and problem solving. We apologized and shook hands, and opinions were respected. Team responsibilities. The overall distribution of work was equal, and as we progressed, we all helped each other out, even in topics outside of our scope. Thank you very much for listening to our presentation, and we hope you enjoyed it.